Okay, so this is example 4.5, number 8, and we're only going to do, let's see, it has, what, ABC, parts A, B, C, D, and E in it. We're going to just do A, B, and C. We're not going to do D and E because very much like some of the other problems we did, D and E are relative motion, and we did those in section 1 of this chapter. So A, B, and C are what we're going to do just for this one right here. Okay, so we've got a boat traveling at a speed of 6.5 meters per second in still water. So I have the boat drawn right here. Actually, let me read the whole thing first, and then that'll make sense why I drew this. It aims directly across the river. So this is the direction of our boat. Okay, the river's current is 4.5 meters per second west, so it's going that way at 4.5 meters per second. So that's why I drew the river horizontally, because if it goes across the river, it must be going north-south if the river is going east-west, like that. So let's write in our values right here. But the water is 4.5 meters per second. Okay, 4.5 meters per second, and the boat is traveling through the water at, I believe, 6.5 meters per second through the water, like that, okay? So what is the boat's velocity and magnitude direction notation relative to the shore? All right, well, we could go back and do relative velocity problems, but I think you can tell this is already set up the way we want it to be. This is the boat's motion relative to the water, right, moving through the water. This is the water's motion relative to the shore, and so adding them together will give us the motion or the velocity of the boat to the shore. I'll say the ground instead of the shore. Boat to the ground. Okay, so the other way we can tell these are already in the right order is that these are already tip to tail. All right, we've got the tip of the boat vector adding to the tail of the water vector right here, and that'll give us our resultant vector here. So what we really want to find out is, at least in part A, what's that velocity right there? All right, magnitude direction notation. Well, we already have what we need. So part A, we have, let's see, this vector, this resultant vector has an x component well, actually, let's do it in unit vector notation. Okay, velocity of the boat to the ground, or the boat to the shore, is what? Well, it is negative 4.5 meters per second x hat, right? Because that's the x component right there, and it is what is it? 6.5 meters per second y hat. All right, so that's how we write it out in unit vector notation, and so that describes that vector right there. Now we just have to put it in magnitude and direction notation. So let's get out our calculators. We'll do our Pythagorean, 4.5 squared plus 6.5 squared. Take the square root of that. So that means that the magnitude vector of the boat to the ground is going to be 7.9 meters per second. At what value? Or at what angle? That would be this angle right there with respect to the horizontal. What would that be? Well, of course, we take the inverse tangent, right? Inverse tangent of the y over the x. So inverse tangent of 6.5 over 4.5. That's 55.3 degrees. Degrees what? That's north of west, right there. That's easy, right? Because we were basically given our components of this resultant vector. We're given the x, we're given the y. All we had to do is our little bit of math right there, okay? So, part B. How long did it take the boat to cross the river if the river is 1.25 kilometers wide? Okay, so now we're introducing not just velocity, but also some displacement into this. All right, so our 1.25 kilometers, that's that width right there. So we can say that's the displacement in what direction? In the y direction, right? Equals, I'll call that delta r y, okay? So how long did it take the boat to cross the river if the river is 1.25 kilometers wide? Well, the key right here is remembering that the x components and the y components are completely independent of each other. Since they're at right angles, neither of them contributes nor detracts from the other one, and so this vector right here, this velocity vector, doesn't care if it's also moving sideways. It just cares that it's moving across the river from this side to that side at 6.5 meters per second. So we have a velocity and we have a displacement. We should be able to solve for the time. Because after all, B is asking for what is the time. And we'll call that t in the y direction right there, just for now. But we're using our y information to solve for it. Okay, so what's the velocity in, oops, sorry about that. What's our velocity in the y direction? Well, we know what that is. That's 6.5 meters per second. All right, what's our displacement? That's an R right there. I'll just erase that. Displacement in the y direction. That is 1.25 kilometers, but we need to change that a little bit, right, because we want meters. So if we move our decimal point to make it meters, it'll be 1250 meters, just like that. Okay, so we have a velocity, we have a displacement, all we need is time. Well, we know the relationship between velocity, displacement, and time. Velocity equals displacement over time, so let's just solve for time. There's a time. If we move it around, that's going to come up on this side. Velocity is going to come down on that side. So we're going to have an equation, a working equation, that is time equals displacement over velocity. Let's just solve. So time in the y direction is, what's our displacement in the y direction? That's 1250. That looks like a 6, but I'm not sure if I can erase that. Bugger, I can't. It's 1250 meters over, what's the velocity? 6.5 meters per second. All right, so our time in the y direction is what? 1250 divided by 6.5. 192.3 what? That's seconds, right? We don't really think of seconds as being in the hundreds, but you can have hundreds of seconds, so that's like, what, a little over 3 minutes right there? Okay, so that's the amount of time it'll take to cross the river. Now, I called it ty because we were using all y components to solve for it. But the key here is that in the same amount of time it takes for the boat to cross the river, it's also the same amount of time for the river to carry the boat downstream. So the point here is that tx, t in the x direction, is going to equal t in the y direction. All right, that's what they have in common. I think I asked you guys to write down some key questions to ask yourself when you're doing problems like this in class. But that's the key issue, and that is the time is what the x component and the y component have in common. So we can apply this exact same time to any motion we have in the x direction as well. So let's do that in part C, because I think it's what C asks for right here. What it asks for is how far downstream is the boat when it reaches the other side. Okay, so not only has it been moving across the stream, but the stream has been carrying it downstream a little bit. So how fast has it been moving downstream? Well, the velocity in the x direction is 4.5 meters per second. I'm keeping the negative out of there for now. We could say that's the negative x direction, but I'll just keep it at the absolute value for now. Okay, and we have the time in the x direction, which is just time for any direction, right? That is 192.3 seconds. So we should be able to solve for the displacement. Oop, I don't want to put y, I want to put x. I'll just make that an x right there. Displacement in the x direction should be pretty easy to solve for, right? Because after all, we know that velocity equals displacement over time. Okay, so as we just bring time up right there, we should be able to solve for displacement. Velocity times time. Okay, so what's the velocity? 4.5 meters per second, and it's been traveling for how many seconds? 192.3 seconds. So our displacement in the x direction Downstream is those two multiplied together. 4.5 times 192.3. 865.4 meters. And there you have it. All right, so we've got the resultant vector of the boat crossing the river and the stream carrying the boat downstream. We got that. We solve for the time it takes for the boat to cross the river if it's going across at a constant velocity and if the river is a certain width. And since we have that time, we can also apply that to the x direction. So that tells us how far the boat has been carried downstream. So there you go. There's example 4.5, number 8. And that's it. Thanks for watching. I'll see you next time.